Welcome back everyone. In the previous section, we covered the basic concepts of what dimensionality reduction is. In this class, we're going to talk about what is PCA or Principal Component Analysis. I've provided two references here for you. One is the scikit-learn documentation itself, and the second one is the parameters that scikit-learn take in for the Principal Component Analysis library that I use. We talked about singular value decomposition of the data and project it to a lower dimensional space. Now, the method here is created by Kyle Pearson back in 1901. Yes, this is the same Pearson correlation. It is an unsupervised machine learning method. We already talked about some of these technology, and we covered this in the previous session, so I won't go into that. Now, there's a few addendum of notes. Typically, when is it used? It's used in exploratory data analysis, also called EDA. It is also used to visualize the distance and relatedness between populations, okay, to see how closely correlated they are. Hence, the background is correlation, which is why we have Pearson there. And the actual method itself, let me just tidy this a little bit. It's eigenvalue, decomposition of data covariance, or you can use either of these methods, either use eigenvalue or singular value decomposition of a data matrix. Typically, that is after normalizing or min centering for each attribute. And what comes out is component scores, typically called factor, and these are also called principal components. They are called the transformed variable values, and also loadings, which is the weight. Don't worry about either of these. We will actually look at this a little bit later. And other usage of PCA, data compression and information preservation, visualization, noise filtering, and also feature extraction, and as well as engineering as well. Now we're going to switch gear a little bit now. I'm going to demonstrate a couple of codes here for you, just so that you can actually visualize how it works. This is a very common method. It's nothing new here, but nevertheless I want to actually just demonstrate to you so that you get a hang of it in terms of the how it actually works. So let's just start with random numbers. Okay, so we're going to generate some random numbers. And we're just going to use the NumPy library called numpy.random, and we're just going to set the random state to 42. There's nothing magic about 42. It's just been around for a long time, and people use it all the time. So now, first of all, I'm going to generate for my x-axis, all right, some values. Okay, so remember, this is the dot multiplication that I showed you. If you're not familiar with this, please go back and revisit what I actually cover in the last lesson towards the last part of it. And I'm going to generate 2 by 2. This is a matrix here, 2 by 2 matrix. So there's 4 elements in there. And also a random number and random normally distributed number, 2 by 500. Okay, and once we've finished with that, I'm just going to transpose that. So let me just show you what it looks like. So this is what we have here. It's basically 2 columns and 500 down. Okay, so the first one, the first column, I'm just going to change it to negative axis. So that is negative sloping minus x, originally 0. Okay, so I just change it to a negative sloping. Now let's plot this using the matplotlib. Okay, x. We're plotting the first one is the x. The first column indexed as 0. First column will be our x. The second column will be our y. Okay. So, and we're just gonna make sure our axis is equal. Okay, so that is proportional. All right, so I don't want this, so let's plot this. Okay, so notice that this is it's a square. Okay, so what we have is a downward sloping. This should be 45 degrees. That's the way we generated it. Now let's just see what it looks like when you actually perform PCA. Okay, so for some scikit-learn, under the decomposition library, we're going to import PCA. Okay, PCA would be the variable, or rather we're going to instantiate this, and we're just going to give two components and fit it into our X data. Remember, X is for both the columns here. All right, the fit is successful. I didn't really set the random state, so that's okay, don't worry about it. So if we print the actual component itself, what you see now is a 2x2 matrix. Okay, interesting, isn't it? So this is basically what the component looks like, and that is the if you remember the description, that's the vector, all right, or the component itself. Okay, now let's move on from there, and let's have a look at the so-called how much of these components actually explain the variability. Now, this is what I printed out, 1.6 and 0.12. Now, typically you don't read this because it relates to the actual scale itself. So what we usually do is that we use the ratio in terms of percentage, which is a lot easier to understand than looking at the purely the actual raw score itself. So what we have here is that the first component explains almost 93% of the variability of the underlying data, and that is really quite crucial and something that we do want to actually pay attention to, and that really is what the strength of PCA is. It literally, from these two, from the raw data, it actually extracted it into two components. Essentially what we're saying here is that, hey, rather than having two components, we just use one component. That's enough. It can actually explain 92% of it. So let me just plot this so that you can actually visualize this. Okay, so what do we see? So we have the length of this is the actual so-called significance of it. All right, remember the 97% or the 1.6 that we talked about earlier? 1.6, where do I get the 1.6? That's this one. Okay, and 0.12 is this length here, so it's much shorter than what it was before. If you look at this, what do you actually see? The first one is the first principal component is this way. The second component is this way. All right, you will remember what I actually mentioned earlier about the idea of PCA is that it's an orthogonal transformation. Or 90 degrees is the way that I explained it. Okay, so you have, let me just provide the explanation here so that you can refer to it. The two components that we have here, the length denotes the actual significance itself. The transformation from data axis to principal axis is also an affine transformation, which basically means that it is composed of a translation, rotation, and uniform scaling. Okay, that's a little bit too much to actually digest, but that's okay. So that's really what I actually wanted to show you, how it can be done, and that's the basic ideas that I want to actually relay. Now, the next question that you're going to ask is, hey, okay, we have extracted two components here, but we already originally have two components anyway. What's the point of doing that? What we're saying here is that we now only have we can just focus on one component, and that actually will actually basically explain most of the variability of the actual underlying data itself. Remember that when we actually generate X, we actually have two features here. Feature 1, feature 2, column 1, column 2. What this is actually saying is that we only need PC1. That would explain 93% of it. You can forget about PC2 if you don't want to actually work with too many features. That's really the basic ideas here. So that's really what we call extracting the principal component, or the component principal component analysis. The second thing that I do want to explain to you, just to cover the basis of, is the dimensionality reduction with PCA. So the first portion here is, let me just come down to this part, and I'm just going to label this. So principal component identification. Okay, just for identification. This step here is to identify the components, and after that, what you can do is up to you. There are actually quite a lot of that you can do with this. Once you actually identify the principal component, you can actually start doing any of these things. Data compression, preserve your information. You know, sometimes for example, our pictures is far too large to store. It was definitely the case in the past. So you can actually run PCA and actually just reduce it and just extract the key components. It could reduce the size by 50%, like what we just did. Instead of having 2 features, we cut it down to 1, and that one preserve 93% of the data. Okay, or you can use it for visualization, noise filtering, feature extraction, and engineering. All right, so having done that, we're gonna do the next part here. All right, so now we're gonna fit our PCA again, except this time we're just gonna set it to 1. Okay, and we'll fit it to our X again, and we're gonna transform our PCA. You can actually fit transform, but I'm just doing this as a 2-step process so that you can see the 2 steps involved here. Run that transform. Okay, that's done. Remember the original shape. We need to have a capital letter. It's 500 by 2. The transform shape is 500 by 1. Okay, so we only have 1 left anymore. Okay, so now what we want to do is just plot this PCA transform, and we're just going to inverse transform X PCA. All right, this is how you actually get your data back, scatter. And we're going to plot our original, which is 0, first column, and X 1, and we're going to plot this as alpha is equal to 0.2, so that is quite faint. Okay, let me just plot this for you so that you can actually see, but before we plot that, we want to make sure the axis is equal. All right, as I did earlier. So if I run that, okay, this is the original data. To convince you, this is the original data. Okay, now what I want to do now is plot over it another scatter plot, sorry, new. This is new, is the inverse transform the XPCA that we did earlier. Again, first column 1, and this time we're going to use alpha is equal to 0.8. Voila, what do you see? The green one is the single component that we are able to extract out from before. That is our component 1, or PCA1, and that preserves bulk of the contents, or the 97% of the contents that we talked about earlier, whereby what do you have? You have a situation whereby you can actually reduce your data by 50%. Remember, this is a dimensionality reduction. By removing the second features, we're just taking the principal component 1. What we can do is that we can run the inverse transformation, and we will be able to bring back about 93% of the actual original contents without much loss of the actual original contents. So that's the basic idea of principal component analysis. So what I want you to do, that's really the core part of what I want to actually share when it comes to this portion here. What I'd like you to do is, hey, maybe just try around with the actual random number. Instead of 500, change it to 5,000. See how much in terms of the variability will change. You might also want to not use a random normal distribution. meaning sampling from a normally distributed population, change it to just random. That will be a uniform distribution rather than a normal distribution, and see what happened. You can of course change it to all the others from binomial, Cauchy. What are the options available? You have beta, bytes, chi-square. Have fun with it. Okay, you can even have gamma. And all these are built in for you to actually generate, and it will give you slightly different pictures because of the distribution. This is normal, so it's fairly nicely distributed around the actual core axis itself. Yeah, so play around with that. Take a few moments. When we come back, I will just wrap up the class itself. Welcome back. I hope you've given that a go and tried it with the other distribution. It should be a really interesting exercise, and just want to wrap up the lesson today. On this part, what we really cover is the basic ideas of PCA, and some of the notes here is for you to refer to. Other things that we talked about really is that it actually identified the key components or the principal components that explains the most variability of your data, and also how you can actually use it to reduce the dimension or reduce or compress your data. And that's really the highlight of PCA. And that's the end of this lesson. What I want to do now is just to explain to you what we're going to cover next. In the next lesson, I'm going to illustrate to you using a ready-made commercial software just to see how PCA can be applied to real-world data, and how to understand or interpret the actual score itself before we work on a real data set ourselves. So with that, I'm gonna stop right now. Thank you for watching. Really appreciate you paying attention. I hope you really enjoyed this. This is probably one of the more exciting topic for me, and something that I find it really, really interesting because it applies to many areas, not just in the basic area that we talked about here. So I look forward to seeing you in the next video. Thank you for watching.